Ladies and gentlemen, we are back with another episode of our hit Solve It series, where you will get complete past paper solutions with explanations that a mere mark scheme or examiner report will not give you. It'll be a quick revision of the entire syllabus, and with a look at the latest paper formats, it will equip you with all that you need to ace your next exam. So, without further ado, let's get started.
Assalamu alaikum everyone, this is Fahd Ansari and I'm here to help you conquer chemistry. In today's video, we'll be looking at the Cambridge International AS Level Paper 2, Variant 2 of the October-November 2022 series. This is the AS Level Structured Questions paper, which is Paper 2, and we are given a time of 1 hour and 15 minutes. And since last year, since 2022, all the data that you need to solve any question involving calculations will be given to you in the question, along with a table of constants and important values and the periodic table at the very end. So we don't even need to open a data booklet for this one. Anyway, so without further ado, let's get started on this paper. All right, so the first question talks about species such as NH4+, CO3 2-, and PO4 3- are examples of molecular ions. So ionic and covalent bonds both involve an electrostatic attraction between different species. Identify the species that are electrostatically attracted to one another in an ionic bond. All right. Now, over here, they're asking about what types of particles attract each other in an ionic bond. They're not specifically talking about the molecular ions that have been given in the beginning of this question, right? So you have to speak in general terms about the ionic bond. So in this situation, you're going to talk about the cation and anion, the positive and negative ions that attract each other in an ionic bond. There's an electrostatic force of attraction between these two types of particles. Now, in a covalent bond, where does the force of attraction lie? Now, we know that in a covalent bond, two atoms share one or more pairs of electrons, right? So the force of attraction is always between the shared pairs of electrons and the nuclei of the two atoms involved, right? So that's what we're going to write over here. The shared electron pair, or we can write pairs, right, because there could be a double bond or a triple bond, and the nuclei of the two atoms in the bond. All right, so that is how you describe a covalent bond. Right, moving on. So we need to complete table 1.1 to show the total numbers of protons and electrons in these molecular ions that we were talking about earlier. Right, now for number of protons, you're going to look at the proton numbers of the elements involved in the molecular ion. For example, for NH4+, nitrogen has a proton number of 7, and hydrogen has a proton number of 1. Since there are 4 hydrogens, so you're going to multiply the proton number of hydrogen by 4. And so when you add these up, you're going to get 7 plus 4 equals 11 protons, right? Now the overall charge on this thing is positive 1. So that means that you're going to have 1 less electron than the total number of protons. So we're going to subtract 1 from 11, that gives us 10. All right. Now, in the next example for the carbonate ion, you're going to do a similar procedure. You have carbon, which has a proton number of 6. For oxygen, it is 8. And you have 3 oxygens, so that's going to be 3 times 8. So you're going to have 6 plus 3 times 8. So that should give us 30. All right. Now we have a 2 negative charge. That means you have 2 more electrons than the number of protons. So 30 plus 2 will give us 32. Next, for the phosphate, PO4 3 minus. All right. We have phosphorus, which has a proton number of 15. For oxygen, it is 8. And we have 4 oxygens this time, so 4 times 8. All right. So 15 plus 4 times 8. And so that should give me 47, if I'm not wrong. All right. So 15 plus 4 times 8 gives me 47. Yep. Next, we have 3 negative charge. So that will be 3 more electrons than the protons. So 47 plus 3 gives me 50. All right. So that's how you have to solve this question. Now it says NH4 plus is a Bronsted-Lowry acid. Define the term Bronsted-Lowry acid. It's pretty simple. According to the Bronsted-Lowry theory of acids and bases, we know that acids are proton donors. So that's all we need to write for the 1 mark, that Bronsted-Lowry acid is a proton donor. Or in place of proton, if you write H plus hydrogen ion donor, that will also work. Right, part 2. When NH4 plus is heated with NaOH, all right, a pungent gas is produced. Write an ionic equation for this reaction. Okay, so we know that NH4 plus is an acid, and we know that NaOH is a base, and specifically the OH minus ion in the NaOH is basic. So when we want to show the ionic equation, we're going to write the NH4 plus, which is the acid, and the OH minus, which has the basic properties in NaOH. That when these two guys react, the NH4 plus will give up its proton, all right? And so when it loses an H plus, you're left with NH3. And that is your pungent gas that is produced, that's ammonia. And when the OH minus gains an H plus, it will form simple water. So that is the ionic equation for this particular acid-base reaction. Right, now it says the nitrogen atom in NH4 plus is sp3 hybridized. sp3 orbitals form from the mixing of 1 2s and 3 2p orbitals, right? So this term over here, sp3 hybridized, in case you're not familiar with how hybridization works, or if you're confused about how to identify the type of hybridization of a given atom in a covalent species, then I highly suggest you to watch this short that I'm going to link up over here. Now, moving on to this question, it says, sketch the shapes of a 2s and 2px orbital. All right, very simple. For 2s, we know that s orbitals are spherically shaped. So we're going to draw a circle, or what looks like a circle, but because we have these 3 axes, we're meant to indicate a sphere over here. Now for 2px, we know that p orbitals are dumbbell shaped, all right? They look like infinity signs if you look at them in 2D. And over here, this is along the x-axis, so that's what we're going to draw. It's going to be along the x-axis. You have 2 lobes, all right, crossing each other at the origin. That's actually where the nucleus is located. Now it says there are many naturally occurring hydrated compounds that contain the anion PO4 3-. We visited this guy before. Now it says name the anion PO4 3-. All right. Now we know that this is phosphate, right? But here's the thing. There's another ion that contains the same elements, phosphorus and oxygen, that looks like this, PO3. It also has a 3- charge, right? Now, how do you differentiate between these 2 ions, right? Well, you could say that this over here is phosphate and this over here is phosphite, But if we're going to use the word phosphate, a better strategy is to indicate the oxidation number of the phosphorus in this ion. Now, in this situation, in order to calculate the oxidation number, phosphorus will be kept as X. Oxygen over here, we have 4 of them, so plus 4 times. Now, oxygen will get the -2 oxidation state because it's more electronegative. The less electronegative phosphorus will get X, and we will add these up to give you -3, the charge on the ion, and X will turn out to be +5. So over here, after phosphate, I will write the Roman numeral 5. All right, that's the full name of this anion. Now over here in part 2, it says that we have a soft hydrated mineral struvite with an MR of 245.3. The anhydrous form of the mineral has the formula NH4MgPO4, all right? And we need to calculate the number of molecules of water of crystallization in the hydrated mineral of struvite, all right? Now what we're going to do is, first of all, you calculate the MR of the anhydrous form of struvite, right? So this is going to be the MR of NH4MgPO4. All right. Now for N, we know that the AR is 14. We have 4 hydrogen atoms, so that's 4 times 1, plus Mg is 24.3. By the way, these values don't need to memorize these. You can find them from the periodic table at the end. And just to save time, I'm not going to keep scrolling up and down from the periodic table. I have enough practice as a teacher, so I remember these values, but you don't need to necessarily memorize these, okay? You can search them up from the periodic table. Right, now phosphorus is 31 plus 4 times 16 for the oxygen, okay? Now, the answer to this question over here, this turns out to be 137.3, all right? This is the MR of the anhydrous salt, okay? Now what we're gonna do is we're going to find the MR of the water of crystallization. Basically what this means is that in 1 mole of struvite, how much is the mass of the H2O that is involved, right? So what we're going to do is we take the MR 245.3 of the hydrated salt minus the MR of the anhydrous salt, and that's going to give us 108. So in 1 mole of struvite, the hydrated salt, we're going to have 108 grams of water of crystallization, right? Now, in order to find the number of molecules, number of water molecules, what we do is just divide this mass that we have got, or the MR of all the waters of crystallization combined, the 108, we divide it by the MR of 1 water molecule. That's going to be 2 for the hydrogen plus 16 for the oxygen, that's 18. And this turns out to be 6. And so the answer will be 6. So the complete formula of struvite is going to be NH4MgPO4 dot 6H2O. All right. Now we have an organic chemistry question so early in this paper already. Normally these come towards the end, but whatever. Let's do it. So over here we have OH minus ions in aqueous solution that react with 2-bromo-2-methyl propane, a halogenoalkane, in an SN1 reaction. All right. Remember that SN1 reactions are for tertiary halogenoalkanes, right? And in this process, the molecular ion over here forms as the intermediate. So now we have to draw the mechanism for the SN1 reaction for the OH minus ions with 2-bromo-2-methyl propane, right? So let's draw the structure of 2-bromo-2-methyl propane. So we have propane over here. We have 3 carbon atoms in the main branch. We have methyl, which is 1 carbon atom in the side chain. And that's going to be CH3. And of course, you have single bonds. And the bromine atom is bonded to the same carbon atom, number 2, in the main branch, as the methyl side chain. So this carbon atom in the middle is bonded to CH3 and Br. And the 2 carbon atoms at the ends will be CH3s to complete 4 bonds for each carbon atom, right? Now in SN1, remember that the SN1 mechanism involves only one reactant in the slow step, the first step. And that is the halogenoalkane itself. The carbon-bromine single bond is first going to break in heterolytic fission, where the both electrons in this bond, the carbon-bromine, are going to go to the bromine. I show this with a curly arrow originating from the single bond and ending up at the bromine. And the reason for this is because the bromine is more electronegative. It has a partial negative charge, and carbon has a partial positive charge. All right? It is less electronegative. So that'll be the first step. Then in the second step, once you have the carbocation with a positive charge over here, next up, well, we have the bromide ion that has been separated, and we have the new nucleophile, which is the OH. All right? And the OH has a negative charge on the oxygen and a lone pair on the oxygen, which attacks the positive carbon atom. So it's a transfer of a lone pair from the negative oxygen in the nucleophile to the positive carbon in the intermediate, the carbocation. And so at the end of the day, the product is just going to be the same thing as the reactant. The only difference is, instead of Br, you have a new nucleophile that has substituted the Br, which is OH. And that's your nucleophilic substitution. Right. Now it says that 2-bromo-2-methylpropane is a tertiary bromoalkane. Yes, we already identified it over here. Define tertiary bromoalkane. All right. So we're going to write this as a bromoalkane in which the carbon atom bonded to the Br atom is further bonded to three other carbon atoms. All right. So that's a tertiary bromoalkane, and we have already seen that this carbon atom over here bonded to the bromine is further bonded to 1, 2, 3 carbon atoms. So that's tertiary. Now it says organic compound M forms when 2-bromo-2-methylpropane is heated with ethanolic OH minus, right? Now there was a reason why I highlighted aqueous over here. When you have aqueous hydroxide ions, that results in a nucleophilic substitution reaction, SN, substitution nucleophilic. Now, when you have ethanolic hydroxide ions, that will result in another type of reaction, that is elimination. And the elimination will be of a hydrogen halide HX. All right? So let me draw the structure of the bromoalkane in question. We have CH3, C, CH3, Br, CH2H. Now the reason why I've drawn it like this is because the bromine will be eliminated alongside a hydrogen from a neighboring carbon atom. It could be any of these three because they're all equivalent. All right? And so I selected this carbon atom over here. So the HBr goes out, it's eliminated, and the two carbon atoms involved will now form a double bond. And so you get an alkene in place. So I'm going to erase all of this, and I get this alkene, which is M. All right? And this turns out to be methylpropane. So that was the end of the first question. Let's move to question 2. So we have some chlorides of some of the elements of period 3. And we have to give the bonding structure and oxidation state of the period 3 element. And these are some instructions. Read these carefully before you see the solution. All right? Pause the video if you have to. Right. Now, over here we need to give the bonding as a letter: C for covalent, I for ionic, M for metallic. Now this M for metallic over here is just to confuse you. All of these chlorides, these are compounds, right? Metallic bonding only exists in metals, metallic elements, not compounds. So it's either going to be covalent or ionic, all right? Now for NaCl, this is definitely ionic, a metal and a non-metal. Silicon chloride and phosphorus pentachloride, these are going to be covalent. Now for AlCl3, now this might be a source of confusion. Now the thing is that aluminium and chlorine have a low electronegativity difference, and so the ionic bonds over here actually have a large covalent character. Okay, so there are two acceptable answers for this. Either you could write this as ionic, all right, because it's a metal and a non-metal, or you could write covalent because you have studied in your syllabus that AlCl3 bonds are covalent because of the low electronegativity difference between aluminium and chlorine, right? Now for the structure, this is either giant or simple. Now for SiCl4 and PCl5, these are very easy. This is going to be simple and simple. For sodium chloride, remember, whenever you have an ionic bonding, that will always result in a giant structure. So G over here. Now, if you had ionic in the previous answer, then you have to write giant, all right? Or if you wrote covalent in the previous answer, then you will have to write simple, right? So these are two possible acceptable answers that you could go for, all right? And now for the oxidation state. Now remember that chlorine is more electronegative than all of these elements, right? So chlorine will get its usual oxidation state of -1. And so according to that, you can calculate the oxidation states of the other element that is present in the chloride. So for sodium, that's going to be +1. For aluminium, +3. For SiCl4, that's going to be +4. Now for phosphorus over here, you have two chlorides, PCl5 and PCl3. For PCl5, this is going to be +5 because you have 5 chlorine atoms, each with an oxidation state of -1. And so when you add them up, you should get 0, right? This is the working that I'm doing in my head right now. You can try it out for the others as well. For PCl3, it turns out to be +3. And for SCl2, this is going to be +2. All right. Now it says write equations for the reactions of NaCl and PCl5 with water. All right. Now remember that whenever an ionic chloride dissolves in water, it's not going to react. It's just going to split up into its ions, right? So for NaCl, I'm going to write NaCl aqueous, right? Because it asks for state symbols as well. It's 3-mark question. The 1 mark is for state symbols. Okay. So this will just split up into ions. It's not going to react with the H2O molecules. So you have Na plus and Cl minus. Easy peasy. All right. Now for PCl5 and all the covalent chlorides for period 3, you have to remember that they don't just dissolve in water. They react with the water and they form an acidic solution. It could be one acid or it could be a mixture of 2 acids, all right? Now, PCl5, when it reacts with water, it's going to give us 2 acids. One is HCl, hydrochloric acid, and the other is going to be phosphoric acid, H3PO4, right? Now, you might be wondering that how would the equation for PCl3 be different? The difference is that PCl3 is going to produce H3PO3. That's phosphorus acid, ending with an OUS. All right. And the difference is again in the oxidation state of the phosphorus, right? As we saw in question 1, all right? Phosphorus has two possible oxidation states. It's either going to be +5 or +3. In this case, because we're dealing with PCl5, we're dealing with the +5 oxidation state, so that will give us H3PO4. Remember the state symbols? PCl5, you need to remember this is going to be a solid at room temperature. Water is a liquid, obviously, and these acids are pretty strong, so we're going to write them as aqueous. And of course, we need to balance out this equation. PCl5 gives us 5HCl, right? And if we check the number of hydrogens, we have 5 over here plus 3, so that's 8. So we need 4 water molecules. That will give us 8 hydrogen atoms. Just to check, we have 4 oxygens on the left and 4 on the right. So that equation is balanced. Let's move on. Right, now it says in the gas phase, AlCl3 gas, this exists at equilibrium with Al2Cl6 gas. All right, this is the equilibrium. Now, in this situation, this is another molecule that's part of your syllabus. 2 AlCl3 molecules are going to combine to give you Al2Cl6, right? So you have these 2 smaller units, we call them monomers. And when 2 monomers combine, you get a dimer, right? Al2Cl6 is a dimer. And the reason why this happens is because AlCl3, when it forms single bonds with the chlorine atoms, let me show this over here. We have dot and cross for the single bond. And because we're using dots for the chlorine atoms, so I'm going to draw 6 more dots for the lone pairs on the chlorine atom over here. So we have Al and 2 Cl atoms over here. Now I'm going to draw another chlorine atom over here, dot and cross, and 6 more dots. So this is AlCl3. Now you can see that Al over here has 6 electrons in its outer shell after sharing. It's not complete. So that is why it will bond with another AlCl3 to complete its outer shell. How? With the help of dative covalent bonds. All right. Now the way we're going to show this is I'm going to draw another AlCl3. Okay. And this Al over here is going to be bonded to a Cl from the first AlCl3, right? And it's going to be bonded to a Cl that's going to be bonded to the first AlCl3. Okay? Now, this might look a little confusing, but let me explain. This Cl over here was part of the first monomer unit. This lone pair got shared with the aluminium from the second monomer unit. All right? So that is an example of a dative covalent bond. Now, this aluminium is further bonded to 3 chlorines of its own. So one single bond over here. Then we have another Cl with another single bond over here. And we have a third Cl over here. Now, the thing is that this first aluminium from the first monomer unit has an incomplete outer shell. So it will complete it by sharing a lone pair from this chlorine atom from the second monomer unit. And that's another dative covalent bond that will help complete the outer shell of the first Al atom. All right. Now all we need to do is to make sure that both Als have 8 electrons each. Yes, they do. And the chlorines on the second AlCl3, we need to fill out their outer shells with 3 lone pairs each. So we're going to draw 3 pairs of dots on all 3 chlorine atoms in the second AlCl3, right? 1 lone pair has already been drawn over here. That's been shared with the first monomer units Al. So we need just 2 more lone pairs on this chlorine atom. All right. Now that is how you draw a dotted cross diagram at AS level, right? It's not just going to be 2 or 3 atoms and that's it, right? It's going to be something a lot more complicated than that. So be ready. State the effect of an increase in temperature on the equilibrium mixture in equation 1. Explain your answer. All right. So you can see over here that this equilibrium shows that the forward reaction is exothermic, right? So if I were to increase the temperature, right, that would mean that according to Le Chatelier's principle, the backward reaction would have to be favored, which is endothermic. It will absorb the excess temperature and bring it back down. All right, it will oppose that change that we have made. So we're going to say over here is that more AlCl3 will form because the endothermic backward reaction will be favored. All right, so now for the next part, we have a 3.3 gram sample of a period 3 chloride, and it's been heated to 500 Kelvin, and the volume of the chloride, which is a gas by now, is 250 cubic centimeters, and the pressure is 323 kilopascals. All right, now we have to calculate the MR of this chloride using this equation. So the problem has been made pretty easy for you by giving you the equation itself. That's not normally given to you in paper 2, but they felt generous enough to give it to you. So now you have a hint. You know where to start. So what we will do first is we're going to see what we know. We know the pressure, we know the volume, we know R, which is a constant, and we know the temperature. It's the moles that are unknown. So we're going to rearrange this to find the moles, which will be PV over RT, right? So pressure over here is 323 kilopascals. Remember, when you're using the ideal gas equation, you have to convert all units to the SI units. So pressure over here will be converted to pascals. So that will be 323 times kilo is 10 to the power of 3 times the volume. Now volume over here is in cubic centimeters, right? We need to convert it to cubic meters. So 250 will be multiplied by 10 to the power of minus 6 because there's a million cubic centimeters in 1 cubic meter, right? You need to remember this. You're going to divide all of this by 8.31, which is the ideal gas constant. This value will be given to you in the exam, and that table I mentioned at the end of the paper, in case you don't remember it, but it's a simple value. Everybody knows 8.31. Anyway, in case you don't know, you can refer to that table. Times T, which is 500. And when you do this calculation, you will end up with 0.0194 moles of this period 3 chloride. All right. And this is to 3 significant figures, keeping in mind that all the data that's been given to me, all these values are to 3 significant figures. But of course, this is a value that's not the final answer, but somewhere in the working. So now the next step that I'm going to do is I'm going to find the MR. Remember, moles equals mass divided by MR. We have the mass, we have the moles. We just need to find the MR. So we will rearrange this. MR equals mass, which is 3.30, divided by the moles, which is 0.0194. Now, you will not actually divide 3.3 by 0.0194. You will store the answer in your calculator and then use 3.30 divided by the answer button. All right. So that stores the answer to a higher degree of accuracy and you will get a more accurate final answer, okay? So this will give you an answer that looks something like 169 0.80, blah, blah, blah. So I'm going to just round this up to 170, right? Keep it to 3 significant figures, all right? Because now this is the final answer, 170. So I can keep this to 3 significant figures according to the data in the question, right? Now, I need to identify the formula of the period 3 chloride. Now, the thing is that I'm going to now subtract the AR of chlorine again and again until I get the AR of the other element that's bonded to chlorine. Now, how do I know when to stop? Well, I should know that in period 3, if I scroll up here, all of these elements will have a lower AR than chlorine itself. Well, because they come before chlorine in the periodic table. Okay? If you want to check the periodic table, you can. All right. Sodium has an AR of 23. Al has one of 27. Silicon is 28. Phosphorus is 31. And sulfur is 32.1. Okay? So all of them have a lower AR than chlorine, which is 35.5. All right? So I'm going to keep subtracting 35.5 from the MR, which is 170, until I get a value less than 35.5. Okay? So you can keep doing this one by one. Subtract 35.5 once, then subtract it again, then again, then again. But I'm going to save us some time and tell you guys that you'll actually subtract it 4 times. And once you do that, you will end up with 28. All right. Now, if I go back up, what does 28 match with? It matches with this guy over here, silicon. It's the AR of silicon, and you have 4 chlorines bonded to the silicon. And so that is the chloride we're going for. So the formula is SiCl4. Perfect. Let's move on. It says an excess of chloride ions is added to 1 cubic centimeter of aqueous bromine. Describe what is observed. Explain your answer. All right. So now we could expect a displacement reaction to occur because you are adding a halogen to a solution of halide ions. But remember that the reactivity of the halogens decreases down the group. And so if you have a more reactive halogen being added to less reactive halide solution, then you will get a displacement. But because bromine is below chlorine, so this is less reactive, right? And because it's less reactive, the chlorine will not be displaced from the chloride solution. So the observation is nothing's going to happen, all right? Bromine aqueous is orange, right? You should know this color. So you're going to say that the orange color of bromine water or aqueous bromine remains unchanged. Now the reason why that is well, you could say that bromine is less reactive than chlorine, but to be more specific as far as AS level is concerned, you could say that the bromine is a less powerful oxidizing agent than chlorine. All right? That's a more specific answer to say. All right? Or you could say that the chloride ions are a less powerful reducing agent, all right, than bromide ions. So that's what we're going to write. Okay, we will write that Br2, or we could just write bromine over here, is a less powerful oxidizing agent because it does not oxidize chloride ions to just chlorine. So bromine is a less powerful oxidizing agent than chlorine. Or you could say it is not powerful enough to oxidize the chloride, right? Or you could say not powerful enough to oxidize the chloride ions. All right. Now it says over here that SCl2 has an MR of 103.1 and it is a liquid at room temperature. SBr2 has an MR of 191.9 and is a gas at room temperature, right? Now you might be thinking that SBr2 is a heavier molecule. Why is it a gas and not a liquid, right? The reason is that SCl2 has stronger intermolecular forces. Now, what type of intermolecular force will we have here? Because you have sulfur and chlorine, you have two different types of atom, and so you're going to have permanent dipole forces. Okay? You have a difference in electronegativity, and as a result, permanent dipoles. So we will say that SCl2 has stronger permanent dipole forces between its molecules. Than SBr2. And the reason why the permanent dipole forces are stronger is because chlorine is more electronegative than bromine, being higher up in the group. And so there's a higher electronegativity difference between sulfur and chlorine. So we will say that Cl is more electronegative than bromine, resulting in a stronger dipole, permanent dipole, of course, in SCl than in the SBr single bond. All right, so that's the reason why SCl2 is a liquid, but SBr2 is a gas. Bismuth is a dense metal in the same group as phosphorus, and we need to draw a labeled diagram to show the bonding, right? So we know that because this is a metal, we're going to have metallic bonding, all right? And so the diagram is pretty simple. You have studied this in IGCSEs as well. What you do is you draw some positive ions that are neatly and regularly arranged in rows, and this is going to be called a lattice. All right, so draw at least 2 rows to show the lattice. Okay, so we will say that this is a lattice of cations. Now we don't know the charge on the bismuth ions as such, right? So not going to mention the charge over here, the exact charge, just know that it's going to be positive. Now around these positive ions in the lattice, you're going to have electrons that are free to move. The technical term that you use for this is going to be delocalized. All right, so you label one electron and you can say that this is part of a sea of delocalized electrons, and that is how the structure of a metal comes about. All right. Now, it says that bismuth reacts with chlorine to form BiCl3. And BiCl3 is a solid at room temperature and it melts when heated gently. All right? So that tells me that it has a low melting point. All right? Then, BiCl3 reacts vigorously with water at room temperature to form an acidic solution. All right? Now, if this chloride reacts with water to form an acidic solution, it hydrolyzes in water in that manner, then we will say that the bonding in BiCl3 is going to be covalent. Covalent because it hydrolyzes to form an acidic solution. And then when we talk about structure, it's either going to be giant or simple. The structure over here is definitely going to be simple. The reason is the low melting point, right? So simple structure because it has a low melting point. And so low melting point points to weak intermolecular forces. All right? And so that results in a simple structure. All right, now moving on to question 3. And now we have good old organic chemistry. Let's go. So, organic compounds can be distinguished using chemical tests and analytical techniques. And over here we have 4 pairs of organic compounds. Now, what do these instructions say? We have to identify a reagent which can distinguish between the compounds in each pair, and we have to give the positive result. All right? That means that when we select a reagent, we have to say what will happen to that reagent if it reacts. And we have to identify which compound shows this result, right? So which compound reacted with the reagent you selected to give the positive result of the presence of that compound. And one other thing, you have to use a different reagent for each test. All right, so let's get into it. So we have organic compounds A1 and A2. Now, A1, you can see that this is an aldehyde, and A2 is a ketone. So how do you tell apart an aldehyde and a ketone? It's pretty simple. You could use either Tollens reagent, or you could use Felling's reagent. Either of them will be able to tell them apart. Now, what will be the observations? Now with A1, which is the aldehyde over here, this is your aldehyde. So what you will say is a silver mirror or black precipitate. This is going to be with Tollens reagent. And in the case of Felling's reagent, you're going to have a brick red precipitate. And this is going to happen with A1, not with A2. All right, because A2, as we saw, is a ketone. All right, now next pair we have B1 and B2. Now both of them are ketones, but the difference over here is that B1 is a ketone with a methyl group on one side. So this is a methyl ketone. Now you can tell apart a methyl ketone from other ketones like B2 using alkaline aqueous iodine or alkaline 2 aqueous, and the positive result is going to be a yellow precipitate, and that is of triiodomethane, and that's going to happen with B1. All right, because it has the methyl ketone. B2 is not going to give you this result. C1 and C2, now C1 is a ketone and C2 is an ester. All right. Now, to tell apart a carbonyl compound, which is the ketone, from the ester, you're going to use 2,4-dinitrophenylhydrazine, or you could just write 2,4-DNPH, and that is an acceptable abbreviation. You don't need to write the full name. 2,4-DNPH. And this is going to give you an orange precipitate with C1, because that's the ketone. That's the carbonyl compound that we are dealing with. Now for the last pair, we have D1 and D2. Now over here, both of them have the alcohol group OH and OH. So you cannot do a reaction of an alcohol. But one difference between them in the functional group department is that D2 contains this guy, the double bond. And the test for a double bond that you know from your IGCSEs is you use aqueous bromine or bromine water. And you could say that it goes from orange to colorless with D2. All right. And so that is going to be the tests that we're going to do to identify these from each other, to distinguish between them. Now it says over here that A1 and A2 are structural isomers. So define structural isomers, okay? All right. So we know that isomers have the same molecular formula, but because these are structural, so I'm going to say but different structural formulae. All right. Now this is the definition that is usually given in the mark scheme, right? You could write that structural isomers are compounds with the same molecular formula but different structural formulae, right? But even if you omit these words compounds with, you should get the 1 mark for this definition. It says give the systematic name of B2. So let's go back up. B2, over here is a ketone, and we have 1, 2, 3, 4, 5 carbon atoms. So that's going to be pentanone. And because the carbonyl group is bonded to carbon atom number 3, and if you start counting from the right to the left, you're going to get the same number 3. So that's going to be pentan 3-one. You have to identify the location of the functional group. Pentan 3-one. Deduce the molecular formula of D1. Go back up again. D1. Right, so over here, let's count the number of carbon atoms. We have 1, 2, 3, 4, and 5 over here. So you have 5 carbon atoms, so that's going to be C5. We have 1 oxygen, so that's going to be O at the end. Now we just need to count the H's. Now the carbon atoms in the corners of the cyclic ring have 2 hydrogens each. So 1, 2, 3, 4, 5, 6. Now this carbon atom over here already has 4 bonds showing up, so it will have no hydrogens. Then we have 1 hydrogen over here, 3 hydrogens over here. So that's going to be 4 more hydrogens, right? So 4 plus 2 plus 2 plus 2. So that is 10 hydrogens. So that's going to be C5H10O. All right. Now it says D2 forms polymer Z when heated gently, right? So let's take a look at D2. Right. Now D2 has this double bond over here, and that will form an addition polymer, right? Easy peasy. So the type of polymer is going to be addition polymer. Draw 1 repeat unit of polymer Z. Now for this, I need to change the orientation a little, right? So I have 2 carbon atoms in the double bond. Now each carbon atom, now this first one is bonded to 2 hydrogens. The second is bonded to 1 hydrogen, and the rest of the structure, which is CH2, CH2OH, right? So I'm going to redraw this monomer here. So this is going to be carbon-carbon double bond, H and H to the first carbon atom, H and CH2, CH2OH. So we need to draw just 1 repeat unit. So what we'll do is get rid of the pi bond. We have a sigma bond left, and we're going to have a single bond over here, square bracket, show the repeat unit beginning, continuation bond, square bracket, to show the end of the repeat unit. This continuation bond is a little longer than usual. The reason is I wanted to draw this ending square bracket, and it wouldn't have been possible if the CH2, CH2OH came in the middle. All right. So that is 1 repeat unit of this polymer Z. All right, so organic compound E contains 3 carbon atoms, and it reacts with cold dilute acidified KMnO4 to form a single compound F with an MR of this much. Now, we have been given the infrared spectra of E and F. And let's see what questions are being asked. By the way, they will now give you the different bonds and the functional groups they're part of and the characteristic infrared absorption ranges for each type of bond within the question. So this will not be part of the data booklet anymore. It's part of the question. All right. Now it says that both spectra show absorptions between 2850 and 2950 per centimeters owing to CH single bonds, right? This CH single bond has this range, and we can pinpoint these particular absorptions on both spectra. All right. For compound E, it's over here. And for compound F, this is the one. These are because of CH single bonds, and that's already been given by the question. Okay, let's move on. It says that we need to use the two infrared spectra and the table 3.2, this table that we just saw, to identify the functional group present only in E. All right, we need to explain the answer referring only to absorptions at frequencies greater than 1500 per centimeter, right? So we have been given a cutoff. Let's take a look at that. So 1500 per centimeters, this is basically where the cutoff exists. And so we don't need to look at anything over here. We just look at everything to the left, all right? Because the wave number increases from right to left. So we only have this particular absorption, and this is at a wave number of approximately somewhere between 1500 to 1600. All right, let's take a look at compound F just to make sure that it's not there. You have the cutoff for compound F over here, 1500 per centimeter. And you can see that you don't have anything in that range. Okay, so now what bond is resulting in this particular absorption or peak? And we can see that in 1500 to 1600, actually till 1680, the C double bond C, carbon-carbon double bond, which is found in the alkene functional group, may result in this particular absorption in compound E. So for compound E, the functional group is carbon-carbon double bond. And the explanation is that you have an absorption between 1500 and 1600 per centimeter. Now let's look at the same thing for compound F. All right. So we have to identify the functional group in compound F this time. And again, we have to look at the absorptions greater than 1500 per centimeter. So let's take a look at this. So the only absorption other than the absorption due to CH single bond is this fat fellow over here. So I will look at the lowest point and go down, and I can see that this is somewhere between 3300 and 3400 per centimeter. All right. So let's take a look. So within this range, over here, we have the 3300 to 3400 that resulted in the absorption for compound F, and that is the OH single bond in the hydroxy functional group. All right. And so the functional group over here, we're going to write OH, and the explanation is we have an absorption between 3300 to 3400 per centimeter. All right. Now it says the mass spectrum of E. Now we're using another analytical technique, mass spectrometry. It shows a molecular ion peak and an M+2 peak of approximately equal abundance at mass-to-charge ratios of 120 and 122. All right. Now we need to determine the relative molecular mass, or MR, of compound E. Now here's the thing. If you have an M peak and an M+2 peak, and the ratio of their heights, or relative abundances, is 1 to 1, they have an equal relative or percentage abundance, then that means that you have a halogen atom, and that means you have one bromine atom. The reason is that you have two isotopes of bromine. There is bromine 79 and bromine 81. And both of them have a roughly equal abundance of 50% each. And so that is why the two molecular ion peaks are a result because of bromine 79, which is the M peak, and the bromine 81, which is M+2. They give equal abundances because of the equal abundances of the two isotopes that cause these molecular ion peaks. Right. So we have a bromine atom. Now, if I go down to the periodic table at the very end, so over here, bromine has an AR of 79.9. All right, so now we're going to use this to find the MR of E. Okay. Let's go back up. All right, so if you remember that compound F has an MR of 154.9. All right, and organic compound E contains 3 carbon atoms. Okay, so you have this information, but now here's the thing. You already have the mass to charge ratios of the M and M+2 peaks, which are 120 and 122. Okay, so 120 is basically the MR if you consider bromine 79 to be a part of that structure. But because we are finding MR, that is found out using the sum of ARs. And the AR of bromine, as we saw earlier, was 79.9, right? That is why instead of going with 120, I am going to go with 120.9. All right. I'm not going to go with 121 because we know that the AR of bromine is not exactly 80, it's 79.9. It's 0.9 units greater than the bromine 79 isotope that was used to calculate the mass to charge ratio for the M peak, which was 120. All right, so 120.9 is going to be the answer for this. Right. Use the information in 3 part C to suggest a structure for E. All right. Now, we know that compound E has a carbon-carbon double bond. So we're going to draw that in. And we know that it has a bromine atom as well. That is part of the structure. And so the rest is just going to be filled in with hydrogens. Okay. And just to be absolutely sure, we can use the MR of the structure, right? We have 3 carbon atoms, so that's 3 times 12. This information was already given to us at the start. We have 1, 2, 3, 4, 5 hydrogens, so that's plus 5, plus 79.9 for the bromine. And so when we calculate the MR, it turns out to be, surprise, surprise, 120.9. All right, so this structure is correct. Now, whenever it says the word structure, you can have a structural formula, you can have a displayed formula, you can even have a skeletal formula. Either of them works, okay? And right now I've drawn a displayed formula. The structural formula could just be CH2, CH, CH2Br. And the skeletal formula would be a double bond, then a single bond. All right, that's 3 carbon atoms, and then a single bond to the bromine. right? So either of them works. If they had specified displayed formula, I would go for this. If it's specified structural formula, this is what I'd go with. If it's specified skeletal formula, this is what I would do. But it says structure, so either of these three will work. All right? Now, next part says that we need to complete the equation for the reaction of E with cold dilute KMnO4. Now this information was already given to us. We know that when an alkene, E will react with cold dilute KMnO4, then F with the OH group that we saw earlier, this is going to form a diol. All right, it's going to have two OH groups added to it. All right, and so if I add to 120.9 the MR of E, I add the MR of two OH groups 2 times 1 plus 16 for each OH. It's going to give me 154.9. And where did we see this before? If you go back up, this is where you saw it, the MR of F. So all our information fits. So this is going to be a diol. So now over here, I will write the structural formula. I will write CH2, CH, CH2Br. And so this will result in a diol. So the first carbon atom gets bonded to an OH. This will be in brackets. And then I have the second carbon atom also bonded to an OH in brackets. And then I will have CH2, Br. I have 1, 2, 3 carbon atoms. That's it. Just to check the balancing, I have 2 OHs added. And this H2O and 1 oxygen atom from the KMnO4 will result in 2 OH groups. Perfect. Now, finally here at the last part of the last question, we have this ester C2 that is synthesized from one reagent A1. Okay? And so, how do we synthesize this? Let's take a look. So A1 over here is an aldehyde. And we know that esters, like C2 over here, can only be made with the help of a carboxylic acid and an alcohol. So carboxylic acid and an alcohol. Now the interesting thing is that the carboxylic acid used over here has 1, 2, 3 carbon atoms, and the alcohol also contains 1, 2, 3 carbon atoms. So this ester C2 is actually just propyl propanoate. And if you look at A1, it has 1, 2, 3 carbon atoms. So this is just propanol. So the synthesis is not that difficult after all. All you need to do is split up A1 into 2 parts. All right. One part you will convert into the acid and the other you will convert into the alcohol. How? Let's write this down. So split A1 into 2 portions. And for the carboxylic acid, we can obtain it from the aldehyde by oxidation. So I will write oxidize 1 portion of A1 to propanoic acid. All right, propanol will be converted into propanoic acid. And for this, we can use K2Cr2O7 aqueous plus H plus aqueous. This is just to show that this is acidified potassium dichromate 6. You could also use acidified KMnO4, potassium manganate 7, with heat under reflux. All right, so mention all the reagents and the conditions for each step, right, as they have told us over here. Okay, and we have to give the organic products of each step, and that is your propanoic acid right here for the first step. Then for the second step, we will convert the propanol into propanol, propan-1-ol specifically. And we could do this by reduction. So we will reduce the other portion of A1 to propan-1-ol using aqueous NaBH4. This is what we're going to use to reduce the aldehyde with heating. Then finally, after these two steps, we're going to react the propanoic acid with the propan-1-ol. And this will be done using sulfuric acid H2SO4 catalyst plus heat to produce C2. That's propanoate. All right. Now, some students, even though at this level you probably already know by now, some students still have the confusion that if you write a little beyond the lines, will it be graded? Yes, it will. All right. You have enough space beneath this part. You can fill this all up. All right. Just hopefully you won't have to ask for extra sheets. They could still be provided technically, but this part isn't that long that you would actually need to go there. All right, so with this, we have concluded the October-November 2022 Paper 2, Variant 2 of Cambridge International AS Level Chemistry. This is the structured questions paper. And if you enjoyed this video, if you liked the explanations to each question, please give it a like. Do comment down below if you still have any questions, and if you would like me to solve any other paper next for the SolveIt series. And of course, do watch all the other videos of the SolveIt series as well. They will be helpful for your other exams. And do subscribe to the channel. And I'll see you in the next video.